to section 4.4, where we are going to expand on what we just learned in 4.3 on our logarithmic functions. We're going to get into our properties, things that we are allowed to do to be able to simplify things in order to do other problems, for instance, to solve equations. So we first have to look at the law of logs. Just like we have the law of exponents, we also have 3 laws that we can incorporate with the law of logs. So let's do that with our first one. We are going to look at what's referred to as the product rule for logarithms. So we are going to let b, m, and n be positive real numbers where b is not equal to 1. So we are going to write the log base b of the product of m and n together. And what can we do to simplify that? Or in this case, we're actually going to expand it out, which helps us in certain cases when we're trying to find the actual equivalent to that. We were going to take log base b of m and add it to log base b of n. So in a sense, you're almost kind of like distributing that, not so much, but you end up having a plus in between there. So that the log of a product is the sum of the logs. So if we practice that here in these next 2 problems, we end up having log base 6, and here's our product between these 2 numbers. Call this m, call that n. We would get log base 6 of 7. Add that to the log base 6 of 11 because the product of it is the sum of the logs. So we end up having that as a final answer. Now, neither one of these are nice. 6 to some power is that 7. Not a nice power. 6 to what power gives me 11? Again, not a nice power. So we would leave it as such in the exact form. Now we come to our log, which is our invisible base 10 here. And I have a product between 2 things. Well, by our property up here, I can split that apart as the log of 100. Add to that the log of x. And again, here's a variable. Can't do anything with that, but notice I do have a number. Now again, an invisible 10 is what I have there. So can I take 10 to some power that's nice to give us 100? And the answer is yes. 10 to the second power equals 100. So therefore, all of this can reduce down to 2. And then add that to log of x. And this would be our answer. Moving into the quotient rule, which is kind of an inverse of a product. So therefore, you might see something that looks familiar as an inverse of an addition, meaning the product here with the addition here. For our quotient rule, we're still going to have b, m, and n be positive real numbers where b cannot equal to 1. Now the reason b can't equal 1, if our base was 1, it wouldn't make any sense because 1 to any power is 1. So you wouldn't know what power it is. So that's why we have that restriction where b can't equal 1. All right, so the log base b of m over n. Now we're dividing 2 things. I can split that up or expand that as the log base b of m, here comes the inverse or the opposite, minus the log base b of n. So each one of these with the product and the quotient rule kind of end up having the opposite of each other. So if you can remember one, do the opposite, you have the other one. So the logarithm of a quotient is the difference of the logs. So we are subtracting them this time. So let's look at this first one where I have a division. Call that m, call this one n. I can then do log base 8 of the numerator minus log base 8 of the denominator. And we can check to see if we can simplify. So 8 to some power, is that nice to get 23? Absolutely not. Here I have a variable. I can't do anything with that. So therefore, that's my final expansion for that problem. Likewise here, now I have the natural log where I'm incorporating those e's. So the natural log of e to the 5th, because this is a quotient, I can then subtract the natural log of 11. Now here, e is the invisible base. E to what power is 11? Who knows? But if I have e to what power is e to the fifth, so e to what power equals e to the fifth, then those exponents better be equal so I can reduce this down to just a 5. That would have been one of our properties from the previous section where these kind of, in a sense, cancel themselves out, leaving me with just that power of 5. And then I'm going to rewrite that natural log of 11 as a final answer for that expansion. Okay? So that was first rule, or first law of logs, and the second law of logs. Here's our third one, which is referred to as the power rule. And we alluded to this a little bit in the previous section with we were solving for those equations at the end. So we're going to let b and m be positive real numbers with, again, b not equaling 1, and we're going to let p be any real number as well. P is going to be represented for our power. Then the log base b of m to the p power. I can take this exponent and bring it out front as p times the log base b of m. So I can now multiply those two things together and have that power out front, which we saw in solving those equations was very helpful to get our x by itself. So therefore, the logarithm of a number with an exponent is the product of that exponent with that logarithmic expression, okay, with that logarithmic number. So here we have 3 instances where we're going to practice using that power, bringing it out front. Now we have to talk about fractional exponent powers here. But here I have a power of 9 by the law of logs that allows me to bring that completely outside and make that 9 times the log base 5 of 3. That's as far as I can go, just practicing bringing that power out front. Now, here we turn to a natural log, but I don't really see a power with that radical, but we have to remind ourselves that with that power, we have a property, so I'm going to kind of revert down here. If I have the mth root of x to the n, remember, that is a fractional exponent of taking our power over our root, so it would be n over m. So power over root. Here, power over root gives me x to the 1/3 power. Now creating that exponent that because of the law of logs, I can bring that out front as 1/3 natural log of x. And that would be my answer for that. Okay. Again, having a power, bring that power out front. Then I have twice of that log of x plus 4. Again, you have a base of 10 here when we don't write it, and that would be our final answer for just expanding out using the power rule for logarithms. Okay? So let's turn to the next page and kind of put some things together. Being able to do this and recognize the powers, the quotients, and the products, you can kind of do the things all at once. So the first thing I'm going to notice is that I have a product of those two things. So with a product, that was rule number 1, I could take log base b of x to the 4th and add that to log base b of, now I'm going to change this with my power over my root as y to the 1/3. With a product, you can separate them or expand them with a sum, a plus. Now, once I do that, I'm going to take care of these powers. I'm going to take care of those powers all at once. I'm going to bring that out, and I'm going to bring that out in front. So this becomes 4 log base b of x plus 1/3 log base b of y. And that would be our final expansion. You want to make sure you take care of, again, the product, the quotient, and the power for logarithms. All right, let's look at this next one. Next one, I see a division, but I also see a product, okay? So you want to make sure that you be very careful there. That division allows me to separate this one with the log and that one. So I'm going to write this as log base 5. Now, this power over root gives me a x to the 1/2 minus log base b of 25y cubed. Okay? So all I did was do that division between the top and the bottom. Now, the problem is I still have a product in this one. So I'm going to separate that now with, here's our x to the 1/2, minus, now I'm getting ready to do two terms. So I'm throwing in a set of parentheses here to say, okay, I'm splitting this up now with a sum of 25, and excuse me, that's not a b, that should be a 5. All right, let me see if I can get real small in here. Right there, that should be a 5. I apologize. Make sure that you go back and change that on your paper. All right, so that should be log base 5 of that, log base 5 of that, plus log base 5 of this y cubed. Now, the reason I put parentheses there is because I have a minus in front, and this minus in front of each of these two terms makes a difference. I have to distribute that through. So I end up getting, now let's see if we can do this. Oh, let's go ahead and bring that power out front. Let's go 1/2 log base 5 of x minus log base 5 of 25. Bring that through, gets a minus, but notice I have a power here, so I'm going to bring that out front as 3 log base 5 of y. Now, each of these first and third terms have a variable. The middle one does not. It is only numbers. So that's where we need to check. Can we go further and simplify that? So the question is, you're looking for a power. Can I take 5 to some power to get 25 nicely? And the answer is yes. 5 to the second power gives me 25. So all of this can be reduced down to 2. And then everything else I'm just going to rewrite because I can't do anything with that. 1/2 log base 5 of x. And that is our final answer. So that one is a little bit more involved. Be very careful. Now, what I also like to say, you can split it like this each time. But if you end up having two divisions in the bottom, look what happens in the end. Both of them are minus. So because we have our quotient rule and we are subtracting those, think about it as if it's in the denominator, you're subtracting off that logarithm piece, okay? All right, so now let's go in the reverse order and write it as a single logarithm. And this is also going to help us kind of work with some equations to be able to do this. A single logarithm means now I'm going to take that plus and bring it back to the product and say, okay, by the product rule, that means I can do log of 25 times 4 because I can multiply them together for the product rule. Well, 25 times 4 is 100. A number with an invisible base of 10, which is a number. Can I take 10 to a power to get 100? Well, I think we already did that one previously. 10 to what power is 100? Well, it is a 2. And that is going to be our answer for that one. The next one, I have a minus between them. And with that minus between them, I know that if I'm going back to a single log, the minus meant that I was to divide these two terms. So I'm going to have 7x plus 6 divided by x, and that is as far as I can go. I've got an x on the top, an x on the bottom. Can't do anything further. Okay? All right, this is our first one. Now, this one looks very similar. I have the minus, so I am going to divide, but notice here I also have a 2 in front. So this is where we had the power that came out front. So when I'm going in a reverse direction, I'm going to take that 2, I'm going to bring it back in as the power. So then I can say, okay, well that's log of x minus 3 squared that I'm subtracting log of x. And now, because I have my minus, we can break that down to the single log of x minus 3 squared all over x. So there's a 2 there. X minus 3 squared all over x. Now, you can, if you want, you can do that all at once. If you recognize to bring the 2 up and do the division, you can go straight from here to here. It's up to you. Okay? Now, let's see if maybe we can do that with this one. I have a power of 2 that needs to come in as a square. I have a power of 1/3 that needs to come in as that. What do we do when we have a plus between them? Well, we can reverse that and bring the product of those two things together. So I get the natural log up. This with the 2 up gives me an x squared. This with the 1/3 gives me an x plus 5 to the 1/3 power, and that is all I need to simplify in one step. Now, if you need to go in pieces, go ahead and do so. Now, this last one is going to be very similar to this one that we had up here. Notice we had a minus and a minus up there. Here we have a minus and a minus as well. So notice that that's going to warrant things happening in the bottom, or dividing by this and dividing by that expression. Now, you might want to go ahead and just kind of do that here by just putting your powers in there. I could write that as log base b of x to the 1/4 minus log base b of 5 squared minus log base b of y to the 10th power. So that gives me all of my powers distributed up. Now I can take this and divide by this and divide by that. So I'm going to end up with a single logarithm getting log base b. I'm going to rewrite that as the 4th root of x. That's what it's equivalent to. Divide by 5 squared, which is 25. And divide by that y to the 10th, I can write it exactly like what we kind of started with in this example that's up here. Okay? All right, very good. So that is expanding and contracting, or expanding out logarithms and bringing logs back down to a single logarithm. Now, the next little section that we have here, we're going to kind of work on solving exponential and logarithmic equations. Both law of exponents and the logarithmic properties will help us in order to accomplish our goals. So what is an exponential equation? Well, it is an equation containing a variable in the exponent. So I might have, from our previous section and from working with our logs definitions, we have things that might be like 4 to the x equals 15. We might have things like 2 to the 3x minus 8 equals 16. And we might have things like 40e to the 6x is equal to 240 or something like that, okay? Natural exponential. Then we also have one here where we can get the same base, and we also have one here that we can't get the same base. So in order to write exponential equations, we want to write it of the form b to the m equals b to the n. And once we have bases that are the same, then we are going to set m equal to n and solve for the variable. So you're going to set your exponents equal to each other. Now, if you can't get the same bases of this on each side, then you have a chart in section 4.3 that we just talked about, where that incorporates the natural log of both sides, which is actually what we're going to do here. All right, so let's look at this first one. The first one has an 8 as a base and a 4 as a base. So the question is, can I write 8 as a base of 4? Well, it's 4 times 2, but that's not a base when we're working with 4 times 4 times 4. So unfortunately, no, you can't. But I could write each one of those numbers as a common base. Remind yourself that 2 squared is equal to 4. But I still have my x minus 3 here. Also remind yourself that 8 is the same as 2 cubed, but I also have my x plus 2 still hanging out there, and my equals. So as long as you can break them down to the same base, you don't have to worry about taking the log of both sides like what we're going to do over here. Now, I do have a base to 2 powers, so by the law of exponents, that means I have to multiply these 2 powers together. So you can write 2 to the 3x plus 2 like this. Has to equal 2 to the 2 times the x minus 3. So we are in this situation here where our bases that are the same. Now I'm going to set those exponents equal to each other as this and that. So therefore, 3 times an x plus 2 has to equal 2 times an x minus 3. And we go from Algebra 1 here to solve as a 3x plus 6 equals a 2x minus 6. And I'm going to choose to subtract 2x from both sides. Goes away. I'm then going to subtract 6 from both sides. That goes away. So therefore, x equals negative 12. And that's going to be my answer. Okay? Now, unfortunately here, we can't have a base that is the same. So we end up having to revert back to getting our exponent kind of by itself. In order to do that, now we have two exponents on either side. I'm first going to divide by 17 to get 17 over here between 19. Now, the other thing I can do, so I have 1.14 to the x equals 19 times 1.16 to the x all over 17. Now, in order to kind of get my x's on the same side, since this is a product of two things, I'm going to choose to divide by that power and divide by 1.1 to the x power. So now this goes away on this side. Now, a lot of exponents again come into play here. We can do fractions. So if I say I have 1 over 2 to the 5th power, that means I can do 1 to the 5th over 2 to the 5th. Now what we want to do in this case is to go backwards. I have individual powers. Can I then rewrite this as 1 fraction to that single power? And that's exactly what we want to do here. So I'm going to write that as 1.14 over 1.16. Now yes, it is not the prettiest fraction, and this is not the prettiest fraction either. So we have this to a power equal to 19 over 17. Now, this is the point where I realize I can't put this in as a same base. So we are going to take the log of both sides when we do that, okay? Power rule comes into play here because now I can take this power. Once I have the log of that to a power, I can bring that out front. And now I get x times the log of 1.14 over 1.16 equals to the log of 19/17. And now, here you got to remember, these are just numbers. They're just constants. 10 to what power is that? Well, it's going to be nasty. 10 to what power is this? It's going to be nasty, but it's just a number. So if I want to solve for x and that's being multiplied, I now need to divide by the log of 1.14 over 1.16. Divide by the log of 1.14 over 1.16. And this goes away, give us 1, and then we have x equals, and this is where you want to bring in your calculator. Making sure that you can do the logs on your calculator. You should have a log button or a natural log button. So I'm going to do log of, I would do parentheses of 19 divided by 17, or you can use a fraction key. Divide that by the log of 1.14 with 1.16, and so what you should end with is negative 6.395 if I round to the nearest thousand. That would be your decimal value to solve that equation. Okay? All right, let's try the last ones that we have here. Another different type of way to solve logarithmic equations. So this is if we have an equation that contains a variable in the logarithmic expression. Okay, so what does that look like on a couple of these? That might look something like log base 4 of 3x minus 2 equals 2. It might look something like the natural log of x plus 2 minus the natural log of 4x plus 3 has to equal the natural log of 1 over x. So notice that each one of these expressions has the x in it. Now, how do we solve that? Here's 4 easy steps to be able to do that. We would like to bring that down to one single log equal to a number. Now, that is where our practice of taking the law of logs right here on this reverse page and writing it into a single log is going to help us. We need to bring it down to a single log. Then we want to write the corresponding exponential function, which we've practiced in the previous section. And then we have to solve for our variables, and we're going to check our solutions because that m has to be greater than 0. That piece right there has to be greater than 0. That is a condition that we've had all along. All right, so let's look at number 1, or this first example. Do we have of the form log base b of m equal to c? Well, yes. We have log base 2 of this expression equals 3. So we can skip step 1 here because we're already in that form. Step 2 says, now I need to rewrite that in the exponential form. So I take my base to this power equals that. So 2 cubed has to equal x minus 4. Well, can we solve that? I hope so. Let's do our 2 cubed to be 8 equals x minus 4. Then I'm going to add over the 4 and get x equals 12. That would be my answer. Is that okay? Is it positive? Yes, it is. That is our answer. Okay. Now we turn to a natural log function or equation. Now notice we have a 4 out front with our log. By the power rule, I could take that 4 and bring it up here, but I will tell you that will become very, very nasty. Here is what I'd like for you to get used to doing. You have a number out front that's times by that expression. Just like if I have 4x equals 8, how do I get x by itself? Well, I'm going to divide both sides by that number. That is multiplied by the expression. So I'm going to divide both sides here by 4 and get ourselves a natural log of 3x is equal to 2. Now again, this is where we're going to go into the exponential form. Reminding yourself that the natural log is the base e, so I'm going to go e squared equals 3x. So e to the second power equals 3x. Now to get x by itself, we're again going to undo by dividing by 3. Therefore, x equals e squared all over 3. And that's our final answer there. Okay? All right, the problem with this guy over here is that I don't have one single log yet. I don't have it isolated by itself. But with a plus between those two things from our very first part here in this section, we could make that the product of those two as one single log. Now notice we don't see a base, so it's assumed to be 10. I'm going to bring in x and multiply it by x minus 3 to equal that 1. So now we are checked with our first little section here. We have, maybe, there we go. We have that log by itself equal to a constant. So now let's go for our exponential form. Remember, that's a 10. So I do 10 to the first power equals that. So 10 to the first equals x times x minus 3. And now it's time to solve. So we've had to do this with quadratics, and so we've talked about how to solve quadratics, and we need that first before we can do this type of problem. So I'm going to first distribute, I'm going to switch sides, so x squared minus 3x, and I'm going to think about bringing that 10 over so I can get 0 on this side. So minus 10 equals 0. Now we have a quadratic that we can factor. So we need to do our two binomials because nothing is in common. I'm going to throw an x and an x down. If the last sign is a minus, they are different. So let's go plus and minus. And because we have a 1, what do we multiply to get 10 that we subtract to get 3? And it's actually a negative 3. What do we multiply to get 10 that we subtract to get 3? Well, we need a minus 5 plus 2. And therefore, what makes this 0 is negative 2. What makes this 0 is positive 5. And now we have to check our condition where what's inside here or what's inside here has to be positive. Well, if I throw negative 2 right into the original piece, that's not going to be positive. So that doesn't work. But if I throw 5 in here, that's good. If I throw 5 and I subtract 3, that's still positive. Therefore, x is equal to 5. All right, let's move into our last section here on how to solve logs that have basically logs on both sides. So we have to rewrite our equation into the form of log base b of m equals log base b of n. So you want to simplify down to where we get logs on both sides and only one log on both sides. Then we're going to set the logarithmic expression equal to each other. So that means that we're going to set m equal to n. Just like we set our exponents equal to each other when we had common bases. Then we're going to solve for our variable. And then this time we have to check two things. I have to check in both sides that n is greater than 0 and m is greater than 0. for each case. Okay? All right, so here we go. We've got 3 of these. Let's finish those up. Finish strong. We're going to first get rid of that 3. I can't really divide that both sides this time because I have this log hanging out. So this is the time, yes, where I'm going to use that power rule and bring that 3 as the exponent of x cubed. So now I have a log of something equals a log of something. So what we have to do is set those somethings equal to each other. Once you have that, go to step 2. Therefore, x cubed has to equal 125. How do I undo a cube? Well, that's taking the cube root of both sides. And therefore, that cancels that, leaves me with an x. And the cube root of 125. Use your calculator, or what times what times what gives me 125? And that number is a 5. Now, does that work? If I put 5 back in here to this expression, it does stay positive. Therefore, that is our final answer. All right, the next one. Log of x plus 7 minus the log of 3 all over the log of 7x plus 1. So I have a minus there. Well, this side is okay. I already have a log by itself of 7x plus 1. I don't have to do anything there. But with this minus, go back to that quotient rule for logarithms. I can say, well, that's equal to the log of x plus 7 divided by 3 because that is our quotient. So using logs, we get this. Once I have a log equal to a log, now we're going to extract out that these two things are equal. So when is x plus 7 over 3 equal to 7x plus 1? Now, how do we solve this equation? Well, I'm going to times by 3. Get rid of that fraction if you can. Times by 3 both sides. This leaves me with x plus 7. And over here, when I distribute, I get 21x plus 3. And I'm going to, let's subtract x, and let's subtract 3 from this side. Going side to side, this leaves me with 4 equals 20x. Now, how do we undo this? Well, we're going to divide by the number next to the letter and cancel this piece. Therefore, x equals, reducing this, gives us a 1 over a 5. Divide top and bottom by 4, that gives it to us. So if I throw 1/5 in here and add 7, that's still going to be positive. If I throw 1/5 in here times 7, I get a positive number. When I add 1, it's still going to be positive. So that is our solution. Okay? And so our last one ends up kind of combining these two ideas together where I have a power that I can bring up front, and then I have a division here that warrants because of that difference. So I would get log of x squared minus the log of 7 equals the log of 112. And once I bring that power up, then I can do this difference and say, okay, well, I can now do the quotient between x squared and 7. So I would get x squared over 7 equals the log of 112. And now if I have a log equal to a log, we can again extract out the logarithmic expression and say, okay, well, that means x squared over 7 has to equal 112. To solve for x, just like we did over here with the 3, I'm going to multiply by 7, both sides. So I get x squared is equal to 784. Now, how do I undo a square? Well, I'm going to undo a square by doing my square root of both sides. And technically, there's a plus or minus that comes with this. So, if I said x squared equals 9, then x can equal 3 or negative 3. Any of those work. So actually, there's a plus or minus here. So if I do a plus or minus there's really a plus or minus. Do this in your calculator, you get 28. But notice, if I have a negative and I try to throw it in here, it has to be positive, so it can't be the negative version. Therefore, x has to just be the positive 28 for my answer. Okay, so double check that. Make sure those m's are the same. All right, come on, get off of that. Okay, so that would be your final answer for that. Okay, all right, so that ends section 4.4 on logarithms. And so Hopefully you found some tools that are nice to be able to solve some of these logarithmic equations. Until next time.